Hello friends, welcome to iitian's Gate classes. Our today's topic is going to be basics of signal conditioning circuit. Basics of signal conditioning circuit. Before we are going to start the signal conditioning circuit, in our generic block diagram of the instrumentation system, where the signal conditioning circuit is there and what all elements we are using in it. So today we are going to cover that. We will cover what all elements that could be there in the signal conditioning circuit and where is basically it's sitting. So if you see this generic block diagram, so on the left side is going to be my input. So input is going to be true value or the physical process that we are measuring. The first block to the instrumentation system is going to be sensor. The next block is going to be signal conditioning circuit. So we will today we will cover what all elements can be possible here in the signal conditioning circuit. Basically it's an electronic circuitry. Electronic circuit basically we are using. Okay, then processing and data presentation part will come. I will take one example of RTD complete block diagram. In that case, you can understand where we are using the signal conditioning element. So what is the aim basically? We will cover these things, but before that, let's take one example of the temperature measurement using RTD. So RTD here we are using as temperature sensor. RTD we are using as the temperature sensor. RTD stands for resistive temperature detector. RTD stands for resistive temperature detector. It will sense the temperature. It will detect the temperature and provides the output as change in resistance. Right. So this is basically made up of a resistive element, and whenever temperature changes, whenever it senses the change in temperature, then it changes its resistance. Right. So this will sense the temperature. More precisely, change in temperature. It will provide the output as change in resistance. Right. So these change in resistance we want to convert, and we want to present this change in resistance here. Not this change in resistance. Basically, what is the ultimate aim? Ultimate aim is to observe the physical variable. Ultimate aim is to observe and control the physical variable. So here we are not controlling at all. Some feedback element will come in the process control, but now we just want to observe the physical variable. And what is the physical variable here? Physical variable is going to be temperature. We want to observe the temperature. So for that we have to convert it into voltage or current quantity, so such that we can either transmit, right, voltage or current quantity. So so for that scenario we are using the two extra elements, that is the signal conditioning circuit. We are using Wheatstone bridge and the op-amp, and both are combined to call as signal conditioning circuit. So what could be the primary aim of the signal conditioning circuit? It will take the sensor output and provide the output that should be in a condition for processing, right? So wherever we are using the processing element, the input of the processing element should be in a very good condition such that it can directly be processed, right? If it is not in a condition, then we have to use the signal conditioning circuit. If it is in a condition, then we can directly use the output of the sensor to the processing element, right? So the aim is that to make the output of the sensor in a condition for further processing, right? Next coming is that what all elements that are there in the signal conditioning circuit. So basically we are using two elements, or more precisely we use three elements. First is going to be Wheatstone bridge. This is most widely used Wheatstone bridge. This is most widely used signal conditioning circuit. To convert our change in resistance, what it will do, it will convert change in resistance to change in voltage quantity. Next element we use as op-amp. Op-amp, or precisely we can say as amplifiers. And what is the basic aim of the amplifier? Is to increase the strength. Increase the strength. Next element we use as filter. And where we are using, basically we just want to suppress some of the input noises, and these applications you will see when we are going to cover LVDT or capacitive sensors, where directly we are interacting with the AC input voltage. where we are directly detecting the input AC voltage, AC supply voltage, right? So first we will take the Wheatstone bridge and we'll see where we are utilizing this and how this is working. So Wheatstone bridge is here. Uh, basically what for what purposes we are using. If you know the structure of the Wheatstone bridge, how it is designed, here we are using the four resistive element: 1, 2, 3, and 4. In any of these fours, you can place your sensor here. So in the previous example here I have taken RTD. So what you will do, you can place your sensor here. You can connect your sensor to these elements, right? You can connect between A and D, or you can connect between any one of the arms, right? And then you can measure the change in voltage from here, right? So you can measure the change in voltage from here, change in the voltage. You can connect sensors in any of the arms, or you can connect to 2, or you can connect to 3, or you can connect to 4. So these all are the basic configurations of the Wheatstone base, depending on how many number of sensors we are connecting in number of arms of the Wheatstone base. So if I have to tell the some of the basic applications, then first application is going to be convert the change in strain to change in voltage, change in strain to change in voltage. And where we are utilizing this, when we will study strain gauge as a sensor, then we are going to connect our strain gauge in one of the arms, or two of the arms, or four of the arms. Then we will get the output as change in voltage. This is the first application. Second application could be when just now we have seen as the RTD, so where we are converting the change in resistance to change in voltage. This application we can cover in the RTD, or even in the thermistor also these conditions are there. Third possible application could be in the inductive sensors or in the capacitive sensor. So in the inductive sensor, so change in inductance, inductive sensors to change in voltage. These applications we are utilizing in the LVDT, or any other inductive sensors, like a variable reluctance sensor also is there. Then the fourth is going to be capacitive sensors. Here it's also, it will convert to change in voltage and capacitive applications. So like that, many more applications are there. So generally you will find in our instrumentation system there are a lot of applications of the Wheatstone bridge, because this is the very basic circuit that is going to take your change in any physical variable and convert to change in voltage. Basically wherever we are having our change in resistance, change in inductance, change in capacitance, so RLC. So wherever RLC elements are there, like if you are using any sensor which is providing the output at change in resistance, you are using any sensor which is providing a output at change in inductance, you are using any sensor which is providing the output at change in capacitance. So in these three scenarios, you have to use your Wheatstone base to convert it into change in voltage, right? So this is the most important application of the Wheatstone base. Next, we will cover what all types of the Wheatstone bridges are there. Generally, you have heard that we are using DC bridges, AC bridges. So there are basically two type of Wheatstone bridges. One is going to be DC bridge and another is going to be AC bridge. The difference is pretty simple. What all elements could be possible in the DC bridge? The first is that what is the supply voltage? Supply voltage is going to be DC. Here supply voltage is going to be AC. The elements that are used here is as resistive element. Here you could use as capacitive element or inductive elements, right? So these all are the some of the applications of the these are the types of the Wheatstone base, AC or DC. Okay. One more thing we can see is has G. G stand for galvanometer, and D stands for detector. So or vibrational galvanometer, vibrational galvanometer, right? So what is the frequency of galvanometer here? DC galvanometer. This is going to be 0 Hz, right? And this is going to be in the range of 5 to 20 Hz. So you can see that direct application, what is the supply voltage, what all elements could be. So wherever we are using in the last slide I have shown you. So in these two applications, inductive and capacitive sensor, we have to use our AC bridges. For these two applications, we have to use our DC bridges, right? So next, coming to what all types of DC breezes are there. Basically, what I told that depending on the number of sensors that you are connecting in the arms, the configuration of the Wheatstone breeze is defined. So when you're using one arm as the sensor and the rest three arms simple resistance, then the configuration is going to be quarter base, right? Quarter means one fourth, right? So out of four resistive elements, or out of the four arms, we are using one of the arms as the sensor, and the rest three of the arms we are using as the normal resistance, right? So this is going to be quarter base, same half base. So we can use these two elements. Remember that we have to use the adjacent elements. These two either you can use, or these two you can use, right? So for that we are using the two sensors here. So 2 by 4. So two of the arms are used as the sensor, and rest two are used as the normal resistance. In the full breeze, you are having all the four as the resistance. So these four we are using as the resistance, right? So 4 upon 4. So 4 out of 4 are used as the uh, sensors, and nothing is the normal resistance, right? So these are all the types of the DC breezes are there. Similarly, we could be having types of the AC breezes. Like the first one is going to be inductive breezes, and the next one is going to be capacitive breezes. Here we can use our inductive sensors. Either if you are using one of the arm as the inductive sensor, then it's going to be quarter breeze. If you use two of the arms, then it's going to be these two you're using, then it's going to be half breeze. If you're using the four, then that's going to be full breeze. Similarly, you could be having here also capacity breeze also. So the difference between AC and DC breezes is not depending on how many sensors you are using in which of the arms. The difference is like what is the supply voltage, which detector you are using, and what type of elements you are using, not the number of elements, right? You can AC or DC breezes, AC or DC breezes, this could be in a configuration of quarter breeze, half breeze, or full breeze, depending on the how many number of sensors you are connecting in the arms. If you're using one of the sensor as the arms, then it's going to be quarter breeze. If you're using two of the sensor in the arms, then it's going to be half breeze. If you're using all the four arms as the sensor, then it's going to be full breeze. But the difference is coming as AC and DC is what all type of sensors you're using, right? If you're using the inductive or capacitive, then you have to use our AC breeze. If you're using the normal resistance, then it's going to be your DC breeze, right? So this is one of the difference. Second difference is going to be what all supply voltages you are using. So supply voltage in the DC is normally DC, in the AC is going to be alternating current. Third is going to be what all detectors you are using. In the DC breeze, you have to use the normal galvanometer having the frequency of 0 hertz. In your AC breeze, you have to use the vibrational galvanometer having the frequency range of nearly 20 hertz or less, right? So this all the first element that we have covered as the signal conditioning element. So what I told in the signal conditioning elements, basically we are using Wheatstone breeze, op-amp, and the third one is going to be filter. So filter mostly you will study in your network theory, and analog also you are going to cover. Op-amp also you are going to cover in the analog. Wheatstone base you will cover in the measurements. When you will study electrical and electronics measurement, in that your Wheatstone base is going to be covered. Full details, uh, how we are going to derive that, and what all applications are there. These all things you will cover here. So I'm not going to cover in details with the op-amp circuit, because these things again you will cover, you will study in the analog circuits. But now just giving the brief overview is that op-amp here, you know the basic op-amp is going to be 741 op-amp. This is the most widely used configuration that we are using as the op-amp, and it's an 8 pin element. It's an 8 pin element, and the basic configuration is like inverting terminal is here, non-inverting terminal is here. So negative is going to be inverting. The name is given as inverting because whatever the signal that you are apply here, you will get the output as inverted. So it's going to be inverting element. Second is going to be non-inverting element. So whatever the signal that you are using here, you will get the output of the signal in the same phase. All right, it's not going to be inverted. So Vs and V minus are going to be the supply voltage of this op amp. So you should not be extending your output voltage beyond the supply voltage. I mean, if the op amp output is getting 10 volts and if your supply voltage is 10 volt, that's fine. But if your output you're getting as 11 volt, if your supply is going to be 10 volts, then your output is going to be saturated at the 10 volts. It's not going to be 11 volts, right? If you're getting minus 11 volt, if your saturation is going to be plus minus 10, so your output is going to be minus 10. It will saturate at the negative V side. So these are the basic concepts you're going to study in your analog circuits, right? So these all are the pin configurations, what all elements we are using. So this second element is going to be inverting, third pin is going to be non-inverting. So 4 and 7 we are using as the supply voltage, 6 we are using as the output, right? So these things you have to remember. So basic applications that we are using as the first is the inverting amplifier. As I told, in the inverting amplifier you are applying the input signal in the inverting terminal of the op amp. So if your input is like this, what will you will get the output? You will get the output as inverted. I'm not considering the amplification part, but amplification depend on the what is the ratio of this R2 upon R1. So basically the output is going to V output equal to minus R2 upon R1 into V input. So based on the ratio of this R2 upon R1, you are going to increase the strength of your signal by that amount, right? So this is the basic aim of the op amp circuit that we are using. The basic aim is to amplify the strength. The first element that we have used is the Wheatstone base, that it will convert to some suitable voltage or current quantity. And then if its strength is not good, then we have to use the op amp circuit to enhance its strength, right? So similarly, we are having the non-inverting amplifier. Its output is going to be 1 plus R2 upon R1 into V input, right? You can take if you have not studied analog circuit as of now, so in that scenario you have to study from your own, do some self study. You can study from Bolstead or Cedra Smith also. You can take help from that books, and you have to practice some of the basic circuits of the op amp, and derive some of the basic circuit, how we are getting the output as V output equal to minus R2 upon R1, how we are getting the output as 1 plus R2 upon R1, right? So there could be other applications like differential amplifier, instrumentation amplifier. So here also you have to go and derive how the signal, how this basic circuit is using, how this signal is getting transmitted to the output part. Then you are getting the output, right? So you have to study this also. You can derive this also. Okay, and instrumentation amplifier, you can also derive that. And so if you're going to derive that, you will understand how the signal is getting transmitted. If you're applying to the positive input, then how the signal is getting transmitted to the output terminal. Like you see, there is no current inside the op amp. This is the very basic fundamental rule, or I can say the parameter or the principle of the op amp, that there is no current inside the op amp. So whatever the current that is coming from here, it will go to the output. That's why you're getting the output here, right? So next is the very important concept is going to be loading. So in a very in a very basic way, I can say is that what is the loading? If you are having one element as A, if you are having another element as B, right, and the output of A is connected to B, you're getting the output here, the input is here. So if you look at this terminal, if you look at this terminal, if this element B is drawing some of the current from A, then B element is loaded by A element, right? If B is drawing some current from A, then A is loading B. A is loading B, right? So this is the very basic concept of what is the loading in our instrumentation. Now I will take one op-amp example, and then I will tell how we are utilizing this concept and what all take cares that we have to do in our op-amp circuits. So I'm taking the first example. Let's say we are having a 10-volt supply voltage here, DC, and then we are using the potentiometer here. Potentiometer is having the resistance of 100 ohms, and just I'm taking some random data, and length is going to be okay, just ignore the length, right? We are connecting the pot or the or its jock to the mid of the resistance. So this side resistance is going to 50 ohms and this side resistance is going to 50 ohms, right? Then we are connecting one op amp here, and this time we are using as the inverting amplifier. Minus plus positive part is grounded. So let's say this is going to be 100 ohms and this is going to be 10 ohms. So what should be the possible output, right? So try to pause the video and try to solve this. So I am trying to solve this. So let's say we are when we don't know anything about the concept of loading, in that case how we can solve this. So you know that when it is connected midway, the resistance is going to be 50 ohms, the resistance is going to be 50 ohms. So if this 10 volt is there, what could be the output voltage here? Just divide this 10 into 50 upon 50 plus 50. V VP, let's say this VP. So VP is going to be 10 into, just voltage division I am applying, 50 upon 50 plus 50. So what is, it's going to be 5 volts. So you are getting the output here as 5 volts. You're getting the output VP as 5 volts, right? So you got VP as 5 volts. Next, this 5 volt you are applying to the op amp, and what is the output of the op amp? Just now we have seen the output of the op amp is going to minus R2 upon R1 into V input. V output is going to be minus R2 upon R1 into V input. And what is R2 here? R2 is going to be 100 ohms minus 100 upon 10 into V input. So V input is going to be VP, and VP is going to 5 volts. What you are getting? Minus 50 volts. As of now, do not consider the op amp saturation, right? Do not consider this op amp saturation. This is just a random data just to understand what is the concept of loading. So but this approach is completely wrong. You should not be getting the output as minus 50 volt. Now I will tell the reason why you should not be getting this. If you see here, the first thing you did is just applied the voltage division. Here you have applied the voltage division, applied voltage division. But think that, can you apply the voltage division here? The answer is no. Why? Because the current that is coming from here, you have assumed that, okay, let me erase this. So the current that is coming from here, you have assumed that all the current will go down to the negative terminal. That's why you have done the voltage division here. But some of the current is also going here, though it's not going here, but it's going to the output part, right? So in that case, you should not be applying the voltage division here. If you are not applying the voltage division, then how you're going to solve this? The most prominent and the effective way is to apply the Thevenin's theorem. Again, this concept you will study in your network theory. So how you are going to apply the Thevenin's theorem? Just Thevenize this first circuit. Just Thevenize the first circuit and then connect to the second circuit, right? So if you Thevenize this potentiometer, then this is going to be RTH, and here this side is going to be my VTH, and then you can connect your op amp. If you Thevenize this, then what happens in the in Thevenization? You are separating the both circuits. You are separating op amp and the separating the potentiometer. So there is no loading effect. No current is going from the output of the potentiometer to the op amp, because you are already disconnecting both of the circuits, right? So in that scenario, you can directly apply the Thevenin's theorem. So how you're going to apply the Thevenin's theorem? What is going to be VTH here? VTH is going to be, right. So you can apply the voltage division to get the VTH, and you can apply the parallel circuits to get your RTH. These things you will study in your Thevenin, in your network theory concept. I'm not going to in details with here. So you can apply the Thevenin's theorem to get your output voltage here, right? So the basic concept that why we are using the Thevenin's theorem, just to avoid the loading effect. In the first scenario where we have directly applied the voltage division, we have not taken care that the output of that the current from the potentiometer is also going to the op amp, and we should not be directly applying the voltage division and then connecting to the op amp. So the best possible way is to Thevenize the first circuit, or if needed, Thevenize both circuits. So here second circuit is not needed to Thevenize. First circuit you can Thevenize. You can separate both circuits. Now there is no interaction between these two circuits in terms of current. You can directly calculate the Thevenin's resistance and Thevenin's voltage. Then you can connect here. Now there is no such loading, and then you can directly apply your formula minus R2 upon R1 into V input. Now what is going to be R2? R2 is same 100 ohms, but R1 is going to be 10 plus RTH. R1 is going to be 10 plus RTH. So so by this you can understand how the concept of loading is there. These things you have to take care, because this is the very basic mistake that every student or some of the students or in fact those who are practicing also, they can do sometimes, because of some they used to forget this concept, right? So you have to think this, and keep on revising. Nothing is very tough. So with this note, we are ending the session. Now, what self-study you can do? You can derive the output of the Wheatstone base. You can practice on the op-amp questions like that. So you take the reference from Cedra Smith or Bolstead, or you can practice previous year questions as well, right? Okay, so we have also started our full courses for our gate instrumentation. If you wish, you can join our team. Dedicated team is there. They are covering the full courses on our online platforms. We are taking the classes online also, so that everybody can attend. Those who are working professionals also, they can attend, right? So with this note, we are ending this. Thank you.